Hello, this is Junsang Park. I will give a presentation of my research titled Deep Reinforcement Learning Based Pin Assignment Optimization of BGA Packages Considering Signal Integrity with Graph Representation. To start my presentation, I will start with introducing the motivations of my research, then introduce the limitations of existing researches related to pin assignments. And then I'll introduce the concept and mechanism of my algorithm, and then explain the performance analysis based on experimental results. So ball grid arrays is one of the widely used packages which provide three interconnections to 3D ICs. And to meet the demand of increasing higher operating frequencies in electrical devices, the number of IOs and interconnections of ICs is growing, and as well as the pin count and density of the BGAs. And this causes signal integrity issues in the BGA packages. And the signal integrity issues of the BGA packages related to the distribution of signal and power ground pins are as follows. The adjacent BGAs will couple with another, which changes the inductance of the BGAs. And also, the local variations of inductance and capacitance in the BGA package triggers impedance discontinuity to the return path of the BGA and also nearby transmission lines. So to mitigate this problem, there have been several researches with assigning pins with existing optimization algorithms, such as genetic algorithm or simulated annealing, and these methods are usually called meta-heuristic methods. They usually set objective function with metrics of signal integrity and power integrity to ultimately design a uniform pin arrangement of signal, power, and ground balls. But unfortunately, these researches can only assign pins with rectangular arrangements. That is, it cannot consider board constraints such as keep-out regions or dummy balls existing in real applications. Also, meta-heuristic methods need to start from scratch on all operations, which makes it very time-consuming. However, we tackle this problem with a different approach, a machine learning method. We build a deep reinforcement learning framework, and this framework takes the BGA grid in the form of a graph and trains a policy that acts as a solver for assigning graph nodes to signal pins and power ground pins. And the concept of representing BGA pins to a graph is a key concept that makes our framework very meaningful. Because by representing the BGAs into a graph, we can formulate the pin assignment problem to a conventional combinatorial optimization problem called the maximal independent set problem. The maximal independent set is a very well-known graph problem that aims to find a set of nodes with the maximum number of vertices or nodes that are not adjacent to each other. So we formulate this pin assignment problem to a variant of the maximal independent set problem with the objective to to spread out the power ground pins. Another advantage that we can take with graphs is that we can still utilize graph representation learning. To say it in another term, we can use graph neural networks for parameterization of the neural network. And the GNN, the graph neural network, extracts important graph properties and embeds it into a set of vectors. And because the graph is transferred to vectors, it enables us to use previous machine learning methods. So finally, we introduce a state-of-the-art reinforcement learning framework for solving the maximal independent set problem. We use this framework as the base framework of our algorithm. And the overall framework, as shown in this figure, is in the form of an actor-critic framework with a combination of the Markov decision process. And each actor network and critic network takes the form of a graph convolutional network. Now I will briefly introduce the Markov decision process, which is the mechanism of the training process in reinforcement learning. And this Markov decision process consists of 4 components: state, action, transition, and reward. And to start off with state, the state is the representation of the nodes or vertices in the graph. Each vertex or node is defined as 0, 1, and star, which indicates the power ground pin, the signal pin, and the deferred states. And when I mean deferred states, it means that the assignment of the vertex is not yet defined, and that the assignment of this particular node is postponed to later steps of the assignment. So there are multiple steps in assigning the pins of the graph. And next is the action. The action 0, 1, and star represents the assignment of the power ground pins, signal pins, and deferred nodes. The action of assigning balls is taken through multiple steps, as mentioned before. And in other words, the action is taken sequentially in multiple steps until the graph is full. And by this, we can solve the pin assignment task as a locally decomposable problem. And this enables us to prioritize easier decisions to be made first, which also simplifies the harder decisions by eliminating the source of uncertainty caused by the undetermined or unassigned neighboring nodes. And we define the transition phase. The transition phase is usually a probability function that chooses the action that takes the previous state to the next state. However, we define a transition phase that constrains the ratio between the signal and power ground pins to the ratio that we target. And there are 2 phases in the transition phase. One is the update phase, where the action takes place, which is introduced above in the before slide. And the other is the ratio matching phase, where a action restriction rule, which is a heuristic rule that we added, forces the number of signal and power ground pins to match the ratio of the number of pins that we want. And finally, which is the reward, which is the last component of our MDP, is defined to minimize the signal integrity effects of the BGA packages. In order to reduce crosstalk and to reduce the variance of inductance and capacitance throughout the BGA package, we need to minimize the number of neighboring signal pins and place the power ground pins as close as possible to the signal pins. Therefore, we define the reward that penalizes the number of adjacent signal pins and encourage the signal and power ground pins to be sparsely arranged. The following is the loss function for the training the policy. And the loss function acts as an objective function or the cost function that the policy is trained to maximize. So the policy aims to be trained based on the reward function to maximize this loss function. But I will skip the details of this loss function because we don't have much time left and this is too much into machine learning. And next is the training conditions of the policy that we use for our validation process. And the conditions of training is as follows. First, the objective is defined as the sum of the number of adjacent signal pins. So the lesser the objective score, the better the performance. Then we set the target ratio between the power ground pins and signal pins to 1:1. And for training data, 1,000 random graphs are generated for training data, while 100 random graphs are generated for validation data, where the graph size is selected randomly from 15 to 20. And as we can see in the graph, we can see that the objective score converges throughout the training, and this implies that the training is very stable. And next, I will introduce the performance analysis of our algorithm and compare it to the results of that of the genetic algorithm. And we conduct this experiment in with multiple scales of graph size from 100 nodes that has 100 nodes and up 500 nodes and up to 10,000 nodes. And first, we can see that the objective score of our method is much less than that of the genetic algorithms. So since the lesser the objective score means better performance, we can see that our method performs much better than the genetic algorithm, which is a meta-heuristic method. And also we can see that the running time of our method is much faster than that of the genetic algorithms, because our method provides immediate solutions based on the inference of the trained policy. However, a genetic algorithm has to start from scratch, has to start from ground level for every operation or run it makes. And lastly, we would like to highlight the scalability of our algorithm, which is very outstanding. This is demonstrated by, we can observe this by looking at the objective score, which maintains around 30% of the size for all the scales tested. So, for example, if the number of graph nodes is 100, the objective score is around 30. And the experimental results for 1,000 nodes of graph, the objective score maintains around 30%, which is around 3,000, which means that our algorithm is very effective in very large scale graphs as well. And we apply our proposed algorithm to the HBM2 ballouts. The top right is the ball arrangement of the actual pins in the HBM2, which consists of 88 signal pins, 48 power ground pins, and 8 differential pins. And we assume that the 8 differential pins are fixed, are predetermined. And then we apply our algorithm to this HBM2 ballout, and the following shows, and as you can see in the figure, the signal pins and power ground pins are effectively distributed. Finally, to conclude this presentation, we designed a reinforcement learning process for the distribution of signal and power ground pins so that a certain cost function is optimized. And the advantage of this algorithm is as follows. I will end my presentation here. Thank you for listening to my presentation. And if you have any questions, please contact the email addressed below. Thank you very much.